The morning of August 17, 1944. Southern England. Colonel Max Wachtel stands at a temporary command post near the Dutch border, reading reports that make no sense. His V-1 flying bombs, the weapons that were supposed to bring Britain to its knees, are being destroyed at impossible rates. 74% shot down in the last week, 82% yesterday alone. The numbers are staggering, incomprehensible. His men are launching over 100 missiles per day. Most never reach their targets. Wachtel had commanded Flak Regiment 155W since its formation in August of 1943. The W stood for Werfer, thrower. His mission was simple in concept, devastating in execution. Rain automated death on London. The V-1 was Hitler's answer to the Allied bombing campaign, a pilotless aircraft packed with 1,870 pounds of high explosive, flying at 400 miles per hour at altitudes between 1,000 and 3,000 feet. No German pilot required. No German life risked. Just launch, flight, impact, explosion. Terror from an empty sky. In June, when the campaign began, the British defenses had been overwhelmed. Fighter aircraft struggled to catch the fast-moving missiles. Anti-aircraft guns fired thousands of rounds with minimal effect. In the first weeks, roughly 60% of launched V-1s reached British soil. London burned. Civilians died. The weapon worked. But something changed in late July. Wachtel's intelligence officers brought him the first reports in early August. British anti-aircraft batteries along the coast were achieving kill rates that defied comprehension. Batteries that previously required hundreds of shells to down a single missile were now destroying them with just a handful of shots. One American battery had shot down 4 V-1s with 8 shells. 8 shells. For kills. The reports included a detail that troubled Wachtel more than the numbers. The shells were exploding in the air around the missiles, not on contact. Air bursts, perfectly timed, creating walls of shrapnel that the V-1s flew into at 400 miles per hour. The detonations weren't random. They were precise, as if the shells knew exactly where to explode. Wachtel didn't believe in magic. He believed in technology, in German engineering superiority, in the weapons his nation had developed through years of secret research. But he also knew what the Allies possessed. Radar, superior numbers, industrial capacity that dwarfed Germany's. And now, apparently, something else. Something his intelligence officers couldn't explain. The British called them buzz bombs. The distinctive pulse jet engine created a droning sound that gave civilians roughly 12 seconds of warning when the engine cut out. 12 seconds to find shelter before 1,870 pounds of explosive arrived. It was psychological warfare, the sound of inevitable death approaching. When it worked, by mid-August, it wasn't working. Wachtel summoned his technical officers. They reviewed the ballistics, the flight paths, the altitude settings. Everything was functioning as designed. The V-1 itself wasn't failing. Something was destroying it with unprecedented efficiency. The officers theorized jamming, new fighter tactics, coordinated barrage fire. None of the explanations matched the data. The shells were detonating with precision that suggested active guidance, not timed fuses or altitude triggers. One officer suggested the impossible. Perhaps the Americans had developed shells with some kind of sensing mechanism, shells that could detect a target and detonate themselves at the optimal moment. The room fell silent. Such technology would require miniaturizing radio equipment to fit inside an artillery shell, making it survive the 20,000 G-forces of firing, and making it work reliably enough for mass production. The Germans had been researching proximity fuses since the mid-1930s. They knew how difficult it was. They'd halted their own program in 1940 when Hitler ordered all research that couldn't produce results within 6 months be terminated. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Americans couldn't have solved it, not in the stressed environment of a fired artillery shell, not at the scale required to equip hundreds of guns along the British coast. It was technologically implausible. Wachtel said as much. The officers agreed. They returned to examining conventional explanations, but the kill rates kept climbing. To understand Wachtel's disbelief, you must understand what the Germans knew about their own research. The Rheinmetall-Borsig Company had been developing a proximity fuse since 1937, designated Zunder 19. The concept was sound. The execution was brutally difficult. The fuse needed to survive being fired from an 88mm cannon, with a shell experienced accelerations that would turn most electronic components into powder. It needed to function reliably in temperatures ranging from minus 40 degrees Celsius at high altitude to plus 60 degrees from air friction. It needed to be small enough to fit in the nose of shell, light enough not to reduce the explosive payload significantly, and cheap enough for mass production. The German prototype used electrostatic principles. The nose of the shell was electrically insulated from the body. When the shell approached a metal target, the changing electrical field triggered a detonator. By 1940, they had achieved sensitivities of 1 to 2 meters and reliability of 80% when fired against a metal cable target. Further refinements pushed sensitivity to 3 to 4 meters with 95% reliability. They were close to production. Then came the Führerbefehl, the Führer Directive. All weapons research that couldn't reach production within 6 months was to be terminated to free resources for Operation Barbarossa, the invasion of the Soviet Union. The proximity fuse program died, not because it was failing, because it was too slow. The program restarted in early 1944 as Germany's situation deteriorated and the need for technological advantages became desperate. By then, it was far too late. Allied bombers were destroying German industrial capacity faster than it could be rebuilt. The skilled workers, the precision tooling, the reliable supply chains, all were disappearing into the chaos of total war. Wachtel knew this history. Every Luftwaffe officer with anti-aircraft responsibilities knew it, which meant he also knew that Germany, with its vaunted engineering expertise and years of research, had failed to produce a working proximity fuse. The Americans couldn't possibly have succeeded. The technological barriers were too high, the production challenges too severe. Mass-producing millions of miniature radio systems that could survive artillery fire was beyond anyone's capability. Or so he believed. What Wachtel didn't know, what German intelligence hadn't discovered despite years of effort, was that the Americans had begun their proximity fuse program in 1940, the same year Germany abandoned theirs. They'd started with British research, with prototypes and principles developed by scientists fleeing German occupation. Professor Patrick Blackett in Britain had proposed putting radar in a shell in October of 1940. It seemed impossible then. It seemed impossible throughout 1941 as American engineers at Johns Hopkins University's applied physics laboratories struggled with the fundamental problems. How do you make radio tubes small enough? The Germans used miniature tubes and hearing aids. The Americans bought them through neutral countries, disassembled them, studied them, and improved them. By December 1941, they had tubes 3 centimeters tall, 1 centimeter in diameter, with glass envelopes thin as paper. Tubes that could survive 60% of test firings at 20,000 G. How do you power them? A standard battery was too heavy, an accumulator too unreliable. The solution was brilliant in its simplicity. A reserve battery activated by centrifugal force when the shell was fired. The shell spun. Centrifugal force pushed electrolyte into the battery. The battery powered the electronics for the 20 to 30 seconds of flight. Just enough time. How do you make it work at scale? This was where American industrial capacity revealed itself. By May 1942, 12 companies were involved in production. Western Electric, Raytheon, Sylvania, Eastman Kodak. By spring 1943, 35,000 workers across 60 plants were assembling components. Daily production reached 40,000 fuses. By August 1944, when Wachtel was reading his impossible reports, American industry had produced over 3 million proximity fuses. 3 million. Not prototypes. Not experimental units. 3 million production models, tested, quality controlled, ready for combat. The German proximity fuse program, restarted in 1944, managed to test fire several hundred prototypes before Allied forces overran the facilities. Several hundred versus 3 million. That was a gap. Not a technological gap, though that existed. An industrial gap. An organizational gap. The gap between a nation fighting for survival and a nation with the resources to solve impossible problems through sheer systematic effort. Wachtel's V-1 campaign had begun with such promise. The first missile struck London on June 13, 1944, 1 week after D-Day. The timing was deliberate. As Allied forces established their beachhead in Normandy, Hitler's retaliation weapon would demonstrate that Germany could still strike at British cities, still spread terror, still force the enemy to divert resources to defense. In the first weeks, the weapon exceeded expectations. Of the V-1s that successfully launched, roughly 60% reached British territory. The Buzz bombs killed over 6,000 civilians in the first months. They forced the British to evacuate over 1 million people from London. They disrupted war production. They proved that Germany, even in retreat, could strike back. The British response was massive and immediate. Fighter squadrons were repositioned. Barrage balloons were deployed across southern England. Anti-aircraft batteries were moved to the coast, creating a gun belt designed to destroy the missiles over water before they reached population centers. In June and early July, it wasn't enough. The V-1 flew too fast for most fighters, too low for reliable radar tracking, too small for easy targeting. The anti-aircraft guns fired thousands of shells and achieved kill rates of roughly 17%. 17 V-1s destroyed for every 100 that entered the gun belt. Then the Americans arrived with their 90mm guns, and their British counterparts deployed their 3.7-inch guns, both armed with proximity-fused shells. The transformation was immediate. In the first week of proximity fuse use, late July, kill rates jumped to 24%. By the second week, 40%. Third week, 60%. Fourth week, 74%. On August 23rd, 82% of V-1s entering the coastal gun belt were destroyed. Wachtel watched his weapon's effectiveness collapse. His launch crews were working at maximum tempo, over 100 missiles per day. The production facilities were delivering. The mobile launch units were operating despite constant Allied air attacks. Everything on the German side was functioning, but the missiles weren't reaching their targets. They were being destroyed in a wall of precisely timed air bursts over the English Channel. His intelligence officers brought him fragments recovered from the French coast, pieces of shells that had fallen short or been dropped by Allied aircraft during coastal attacks. The fragments showed evidence of small electronic components, tiny vacuum tubes, unfamiliar circuitry. One report suggested the shells contained a miniature radio transmitter and receiver. Another report dismissed this as impossible given the constraints of size and the stresses of artillery fire. Wachtel faced a choice: believe the impossible evidence, or trust the assessment that such technology couldn't exist at production scale. He chose the latter. German technical experts had confirmed it. The level of miniaturization required was beyond current capabilities. The reliability needed for mass production was unattainable. The Americans might have a few experimental units, but they couldn't possibly be equipping entire batteries with such advanced munitions. The kill rate climbed to 79%, then 82%, then, on one day in late August, 90%, 90%. For every 10 V-1s his crews launched, 9 fell to the coastal guns. Only 1 reached British territory. And of those that made it to the gun belt, British fighters and inland defenses destroyed many more. The weapon that was supposed to bring Britain to its knees had become a demonstration of Allied technological and industrial superiority. September 1944. Antwerp, Belgium. The Allied capture of Europe's second-largest port should have been a strategic catastrophe for Germany. Instead, it became an opportunity. The port sat just within range of V-1 launch sites in the Netherlands and Western Germany. If Antwerp could be destroyed or rendered unusable, the Allied advance into Germany would stall. Supply lines would collapse. The Wehrmacht would gain precious time. Wachtel's regiment, now reorganized and redesignated as part of the reformed 5th Flak Division, received new orders. Forget London. Target Antwerp. Over 2,500 V-1s and V-2s would be launched at the Belgian port over the following months. Destroy the docks. Sink the ships. Break the supply chain that was feeding Allied armies on Germany's frontier. The campaign began with tactical adjustments based on hard lessons from the London offensive. The V-1s would fly lower, between 1,000 and 1,200 feet, making radar detection more difficult and reducing the time anti-aircraft batteries had to engage. They would launch from more dispersed sites, making Allied bombing less effective. They would come in larger waves, overwhelming defenses through sheer numbers. The first attacks in September showed promise. Antwerp's defenses weren't yet fully established. Some missiles got through. Damage was inflicted. Then the Americans arrived with their 90mm batteries, and the pattern from London repeated itself. The British 11th Armored Division, defending Antwerp, came under sustained V-1 bombardment. The defense batteries needed modified proximity, fuses calibrated for the lower altitude attacks. The modifications were designed at the Applied Physics Laboratory in Maryland. They were rushed into production at the Crosley Corporation factory in Cincinnati, Ohio. British Prime Minister Winston Churchill personally authorized a special flight of Lancaster bombers to transport the fuses from Cincinnati to Antwerp. The journey took 3 days. Within a week of arrival, the modified fuses were in action. 48 of the first 75 V-1s facing a single American anti-aircraft battalion were destroyed. 64% kill rate, with a brand-new fuse modification deployed in combat for the first time. By the end of September, the overall interception rate around Antwerp approached the numbers from London. Over 70% of missiles destroyed before impact. Wachtel's staff compiled the statistics. Since June, Flak Regiment 155W and its successor units had launched over 9,000 V-1s at Britain and roughly 2,500 at Antwerp. Total missiles launched, approximately 11,500. Total confirmed impacts on target, fewer than 3,000. An effectiveness rate of roughly 26%. Nearly 3/4 of the weapons were destroyed in flight. The numbers told a story Wachtel couldn't fully accept. His weapon worked. The V-1 was mechanically reliable, reasonably accurate for an unmanned system, and capable of causing significant damage when it reached its target. But it wasn't reaching its target, not because of design flaws or operational failures. Because the enemy had developed a defensive technology so effective it rendered the entire offensive concept obsolete. What made the defeat particularly bitter was that German technical intelligence knew, by autumn 1944, exactly what they were facing. Unexploded shells with proximity fuses had been recovered from Normandy beaches after the Allied invasion. The shells weren't supposed to be used over land where the Germans might capture them, but in the chaos of combat, some American batteries violated the restrictions. A few duds fell on German-held territory. The shells were sent to technical evaluation centers. Engineers carefully disassembled the fuses. They found 5 miniature vacuum tubes, each roughly the size of a pill. Capacitors smaller than a grain of rice. Coils wound with wire thinner than human hair. A battery system activated by centrifugal force. A radar transmitter operating at approximately 180 to 220 megahertz. A receiver tuned to detect reflections. An amplifier to boost the return signal. A detonator with triple safety mechanisms. The technical reports were comprehensive and devastating. The Americans had achieved a level of miniaturization that German industry couldn't match. The vacuum tubes alone represented manufacturing precision that required specialized tooling Germany no longer possessed. The assembly demanded thousands of skilled workers operating under microscopic inspection standards. The quality control needed to ensure reliability at scale exceeded Germany's remaining industrial capacity. One report, filed by a Rheinmetall engineer who'd worked on the German proximity fuse program, included a telling assessment. The minimum time to create equivalent technology would be at least 3 years, assuming unlimited funding, priority allocation of scarce materials, and no bombing disruption. None of these conditions currently exist or will exist before war's end. 3 years. Germany would be fortunate to survive 3 more months. But the most damning detail wasn't the technology itself. It was the scale. The captured fuses bore production markings indicating they came from multiple manufacturers. Western Electric, Raytheon, Sylvania, different factories, standardized components, interchangeable parts, mass production of the highest order. The Americans weren't making a few thousand experimental units. They were producing millions. German intelligence estimated, based on observed usage rates and combat effectiveness, that the Americans had manufactured between 2 and 3 million proximity fuses by autumn 1944. The actual number was higher. Over 22 million would be produced before war's end. But even a conservative German estimate revealed the impossible gap. Germany's restarted proximity fuse program had managed several hundred test firings. America had produced millions of combat-ready units. The reports reached senior Luftwaffe commanders. They reached the Air Ministry. Some reached Hitler himself, though he dismissed them as defeatist exaggeration. The Führer refused to believe that American industry, that mongrel nation of immigrants and capitalists, could surpass German engineering. The reports must be wrong. The numbers inflated. The technology assessment is pessimistic. Wachtel had no such illusions. He commanded anti-aircraft units. He understood fire control, ballistics, and target engagement. He knew what a 90% interception rate meant. It meant the defense had achieved near total dominance. It meant the offense was no longer viable. It meant his weapon, the Virgil tongue swab, the vengeance weapon, had become an exercise in futility. By October, Allied ground forces had overrun most of the V-1 launch sites in France. The mobile units retreated to the Netherlands and Western Germany. Launch rates declined. The missiles that were fired increasingly targeted Antwerp rather than London, which was now beyond range. The campaign continued, but everyone involved understood it was achieving nothing strategic. The port of Antwerp remained operational. Allied supplies continued flowing. The German frontier was being breached. The men of Flak Regiment 155W renamed Flakdrip Park West in another futile attempt at operational security, continued launching. Orders were orders. The V-1s still flew. Some still reached their targets. But the crews knew. They could calculate the odds as well as their commanders. Launch 100 missiles. Expect 10 to reach the target zone. Hope for 5 to actually impact something valuable. The other 90 disappeared into walls of proximity-fused shrapnel over the Channel or over Belgium. One launch crewman, interviewed decades later, described the growing sense of pointlessness. We'd hear the pulse jet engine start. We'd watch the V-1 climb away toward the coast. We'd mark it in the log. And we'd wonder if this one would be the 1 in 10 that made it through. Usually it wasn't. You could almost hear the shells waiting for her out there over the water. Those American guns. They never seemed to miss. The Luftwaffe technical staff compiled increasingly detailed reports on the proximity fuse threat. They attempted to develop countermeasures. Radio jamming was tested. If the fuse operated on radio frequencies, jamming those frequencies should cause premature detonation or failure to detonate. Portable jammers were built for tank units and fortified positions. Field tests near Remagen showed limited effectiveness. Roughly half the proximity fuse shells still functioned normally. The fuses apparently operated on variable frequency windows that differed between production batches. Blanking the entire spectrum required power levels that would make the jammer a beacon for Allied artillery. Mechanical protection was attempted. Additional armor on trenches, protective nets, reinforced shelters. These helped marginally. Shrapnel from air bursts could be deflected or absorbed. But such protection was heavy, expensive, and reduced mobility. For troops in the field, there was no practical defense against shells that exploded 20 to 50 feet overhead, showering fragments downward into foxholes and trenches that provided excellent protection against direct hits, but none against air bursts. By November 1944, German soldiers were learning to fear American artillery in a way they'd never feared it before. The old-time fuses required observers and calculations. You could hide in dead ground, in reverse slopes, in positions the enemy couldn't see. The new fuses didn't care if you could be seen. They detonated above you regardless. Some units reported soldiers refusing to leave their bunkers during artillery barges, knowing that the open ground offered no protection against the rain of fragments from above. The psychological impact matched the physical devastation. This was a weapon that seemed almost intelligent, almost malicious in its precision. It found you. It detonated at the perfect height. It killed you efficiently. There was a helplessness to it that traditional artillery didn't create. Against conventional shells, training and experience and good fieldcraft could keep you alive. Against proximity fuses, you could only hope the shell passed over someone else. The Battle of the Bulge, Germany's last major offensive in the West, began with artillery preparation using conventional fuses. The American forces defending the Ardennes were caught off guard, thinly spread, inadequately supplied. German armor broke through the lines. For the first few hours, the offensive succeeded beyond expectation. Then American artillery received authorization to use proximity fuses over land. The authorization had been delayed for months due to security concerns. If duds fell on German-held territory, the technology would be compromised. The enemy might reverse engineer it or develop countermeasures. Better to keep it secret. Restrict its use to overwater engagements where failures would sink into the sea. But the Ardennes offensive changed the calculation. American forces needed every advantage. General Dwight Eisenhower demanded access to proximity fuse artillery shells. 200,000 shells, codenamed Posit, were already in Europe. The embargo was lifted on December 19th. 3 days into the battle, the effect was immediate and catastrophic for German forces. American artillery batteries switched to proximity fuses and began firing airburst patterns over German positions. Shells exploded 30 to 50 feet above the ground. Fragments rained down on troops who'd felt safe in foxholes and trenches. Detonations walked across assembly areas where units prepared for attacks. German soldiers caught in the open were cut down by the dozens. One American artillery battalion, supporting the defense of Bastogne, fired a barrage at a German battalion attempting to cross the Sauer River. When the smoke cleared, American forward observers counted 702 dead, 702 casualties from a single battalion scale fire mission. General George Patton would later write that the proximity fuse required a revision of the tactics of land warfare. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. German after-action reports from the Ardennes offensive described the proximity fuse artillery as devastating, impossible to defend against, and psychologically crushing. Some units reported minor mutinies when soldiers refused orders to advance through areas under American artillery fire. The traditional protection of entrenchment had been neutralized. Being in the open was suicide. Being in a foxhole was only slightly less suicidal. There was nowhere to hide from shells that exploded overhead. By early January 1945, the Ardennes offensive had failed. German forces retreated to their start lines. The proximity fuse wasn't the only factor in the defeat. Allied air superiority, overwhelming material advantage, and German fuel shortages all contributed. But the artillery effectiveness had shattered German units in ways that conventional bombardment never had. The kill ratios were 3 to 7 times higher than with time fuses. The psychological impact was incalculable. In January 1945, German technical intelligence completed its comprehensive analysis of captured proximity fuses. The report, approximately 50 pages long, was titled Analysis of the American Radar Proximity Fuse, Model 1944. It was submitted to senior leadership with a cover memorandum that began, "What we considered impossible, the Americans are producing by the millions." The report detailed every aspect of the technology. The miniature vacuum tubes, 3 times smaller than German equivalents. The capacitors the size of grains. The coils wound with wire thinner than hair. The battery activated by centrifugal force. The detonator with triple safety systems. The level of miniaturization indicating production capabilities Germany did not possess and would not possess. The conclusion was unsparing. Assembly precision is at the micron level. It demands special tooling and thousands of skilled assemblers. The minimum time to create equivalent technology is at least 3 years. Therefore, the Americans have been working on this since 1941. We would need 1 year for a prototype and another 2 years to ramp production, assuming unlimited funding, priority allocations of scarce materials, and no bombing disruption. None of these conditions exist. The report noted that even if Germany began immediately, there was no time. The Red Army was 70 kilometers from Berlin. Anglo-American forces were crossing the Rhine. The war was lost. Even if they started today, the technology would arrive years too late. A parallel report from Japanese technical intelligence reached similar conclusions after analyzing fragments recovered from Pacific naval battles. Captain Yoshio Kodama, who'd initially doubted mass production was possible, wrote a terse assessment. The enemy's technological level exceeds our capabilities by 10 to 15 years. Reproduction is unrealistic even in peacetime. Both Germany and Japan possessed the theoretical knowledge to develop proximity fuses. Both had started research programs in the 1930s. Both had encountered the same fundamental challenges: miniaturization, ruggedization, mass production, reliability. Germany had halted its program in 1940 due to other priorities. Japan had continued research but never solved the production challenges. America, starting later but committing fully, had solved every problem through systematic engineering and industrial scale. The gap wasn't primarily one of scientific knowledge. It was a gap of industrial capacity, organizational competence, and sustained commitment. The British provided the initial concept. The Americans translated it into 200,000 fuses per month by mid-1944. That was the difference. That was why 74% of V-1s fell from the sky. That was why German soldiers refused to leave their bunkers. That was why the Ardennes offensive collapsed under artillery fire that seemed to come from an enemy fighting a different kind of war. By February 1945, the V-weapon campaign was effectively over. The last V-1 launch site within range of Antwerp was overrun on March 29th. The last V-1 fired at any target fell 2 days later. Flak Regiment 155W had been absorbed into the 5th Flak Division W, and Max Wachtel had been promoted to division commander. His final responsibilities involved supervising the last scattered launches from sites in northern Germany, attacks that achieved nothing of military value. The statistics were compiled after the war. Approximately 9,521 V-1s launched at Britain. Approximately 2,448 launched at Antwerp and other targets in Belgium. Total, just under 12,000 missiles. Of these, roughly 3,200 reached their intended target areas. Approximately 73% were destroyed in flight by fighters, anti-aircraft guns, or barrage balloons. The proximity-fused anti-aircraft guns accounted for the vast majority of kills. In the final weeks of the campaign against London, guns equipped with proximity fuses achieved kill rates of 79%. Around Antwerp, where the Americans concentrated their 90mm batteries with the most advanced fire control radars and the newest proximity fuses, kill rates exceeded 90% on multiple occasions. One day in late October, radar detected 104 V-1s approaching Antwerp. 68 were destroyed by proximity fuse shells. Of the 36 that penetrated the gun belt, only 4 reached the city. 4 out of 104, a 3.8% effectiveness rate. The V-1, the weapon that was supposed to demonstrate German technological superiority and break British morale, had instead become a demonstration of Allied technological dominance. It had forced the deployment of defensive resources. Certainly, it had killed civilians and damaged property. But it had not changed the strategic situation in any meaningful way. It had not stopped D-Day. It had not prevented the Allied advance. It had not saved the Third Reich. And the reason it failed wasn't German incompetence or poor planning. The V-1 itself was a remarkable achievement, the world's first operational cruise missile. The reason it failed was that the enemy had developed a defensive technology so effective it rendered the entire weapon system obsolete before it could achieve strategic impact. Wachtel survived the war. He was captured by Allied forces, interrogated about the V-weapon program, and eventually released. In later years, he rarely spoke about his wartime service. When pressed, he would acknowledge that his command had launched thousands of missiles and achieved minimal strategic effect. He would note that the British and American defenses had been extraordinarily effective. He would sometimes mention, almost as an aside, those remarkable American shells that seemed to know exactly where to explode. He never said the word impossible again when discussing Allied technology. He'd learned the hard way that impossible simply meant We haven't figured out how to do it yet. And in a war between industrial powers, the side that figured out first built it faster and deployed it in millions won, not through superior courage or better training or more motivated soldiers, through superior engineering translated into superior production at a scale that overwhelmed all opposition. The proximity fuse, a technology so secret it was classified above many atomic bomb program details, a technology that saved thousands of Allied lives, a technology that forced German and Japanese commanders to confront an uncomfortable truth. They were fighting an enemy with technological capabilities they couldn't match, industrial capacity they couldn't compete with, and organizational competence they couldn't replicate. When 90% of your V-1s fall from the sky before reaching their targets, you learn humility. When shells explode overhead with precision that seems impossible, you learn respect. When your best engineers tell you the enemy has achieved what you thought couldn't be done, you learn that the war was lost before you even understood what you were fighting. The aftermath of the V-weapon campaign revealed itself slowly, in fragments scattered across the ruins of the Third Reich. When Allied intelligence teams entered Germany in the spring of 1945, they found proximity fuse research facilities that had been hastily abandoned. At Rheinmetall-Borsig's testing grounds, they discovered approximately 1,000 prototype electrostatic proximity fuses. 1,000. The entire output of Germany's renewed research effort from early 1944 to the program's termination in March 1945. The German fuses worked. Test firings demonstrated sensitivities of 10 to 15 meters and reliability approaching 95% when fired at stationary cable targets. The technology was sound. The execution was competent. Given another year, perhaps two, Germany might have achieved limited production. But the war didn't give them another year. It didn't even give them another month. The contrast told the entire story. Germany, 1,000 prototypes over 15 months. America, 22 million production units over 3 years. Not 22,000. 22 million. The gap wasn't technological. It was industrial, organizational, civilizational. It was a gap between a nation devoting its full industrial might to solving a problem and a nation trying to resurrect a canceled program while its factories burned under Allied bombing. The interrogations began immediately. Allied intelligence officers wanted to understand German thinking, German capabilities, German reactions to the proximity fuse. The transcripts revealed a pattern. Initial disbelief giving way to grudging acknowledgement, giving way to something approaching awe at the scale of American production. One Luftwaffe technical officer, when shown a warehouse containing thousands of captured proximity fuse shells, reportedly stood silent for several minutes before speaking. We thought you might have hundreds, perhaps thousands for critical operations. But this, he gestured at the rows of munitions crates. This is insanity. Beautiful insanity. How did you even organize it? The answer was complex, but fundamentally simple. America organized it through systematic industrial mobilization, through bringing together universities, corporations, and military procurement in a collaborative framework that Germany's more rigid hierarchical structure couldn't replicate. Section T of the National Defense Research Committee coordinated 35,000 workers across 60 plants. Western Electric managed production. Johns Hopkins Applied Physics Laboratory handled research. The Navy integrated the weapons into fleet operations. The Army adapted them for land use. Each component of the system worked efficiently because the overall system was designed for efficiency. Germany had brilliant scientists. It had skilled engineers. It had workers who could produce precision components under the most difficult conditions. What it didn't have by 1944 was the organizational capacity to translate isolated excellence into mass production. The proximity fuse required not just technical knowledge, but sustained investment, protected production facilities, reliable supply chains, and time to refine manufacturing processes. Germany had none of these by the time it restarted the program. The statistics of the V-weapon campaign focused on missiles destroyed and targets hit. But behind those numbers were human beings whose lives were saved or ended by technology they didn't understand and couldn't see. In London, approximately 6,184 civilians died from V-1 attacks. Another 17,981 were seriously injured If the proximity fuse hadn't been deployed, if the interception rate had remained at the pre-July 1944 levels of 17 to 20%, those numbers would have been 3 to 4 times higher. Thousands of additional deaths. Tens of thousands of additional casualties. The proximity fuse saved lives. British lives. Allied lives. Lives of people who never knew that miniature radar systems inside American artillery shells were the reason they survived. Around Antwerp, the calculus was similar. The port was critical to Allied logistics. If the V-1 campaign had achieved even moderate effectiveness, if 30 or 40% of missiles had reached the docks instead of 3 or 4%, the damage to shipping and supply infrastructure would have delayed the Allied advance into Germany. Delay meant additional months of war. Additional months meant additional casualties on all sides, military and civilian. The proximity fuse shortened the war, and in shortening it, saved lives. But there was another side to this accounting. The German and Japanese soldiers and airmen killed by proximity fuse shells and anti-aircraft fire didn't choose to fight a war where the enemy possessed technological advantages they couldn't match. The young men launching V-1s from mobile ramps in the Netherlands weren't responsible for Hitler's decisions or Germany's strategic situation. They were following orders in a war they were losing, using weapons that were being destroyed at rates that made their efforts futile. The Japanese kamikaze pilots flying into walls of proximity-fused anti-aircraft fire over Okinawa were told they were saving the homeland through sacrifice. They didn't know that American destroyers were equipped with shells that would detonate themselves when the aircraft came within lethal range. They flew into a technological meat grinder, believing their courage and determination mattered. Courage mattered, but not against radar-guided detonation at optimal kill distance. Approximately 30 to 40,000 enemy soldiers and airmen died from proximity-fused munitions during the war. Most never saw what killed them. They saw air bursts, sudden explosions in empty sky, or above their positions, and then fragments arrived faster than thought. There was no final confrontation, no chance to fight back, no possibility of affecting the outcome through skill or bravery. Just technology, precise and impersonal, ending lives efficiently. War is horror, regardless of the tools used. But there's something particularly modern about death from proximity-fused shells. The weapon that kills you isn't guided by human hands in the final moment. It's guided by electromagnetic waves, by reflected radio signals, by circuitry making decisions at electronic speeds. The person who fired the shell might be miles away, might never know whether the shot killed anyone. The technology mediates everything, insulates everyone from the direct act of killing, makes the entire process abstract and statistical. This was the future. This was what warfare would become. Increasingly automated, increasingly precise, increasingly divorced from human decision-making at the moment of lethal effect. The proximity fuse was just the beginning. Guided missiles would follow. Cruise missiles, smart bombs, drones, autonomous systems. Each iteration removing humans further from the immediate act of destruction while making the destruction more efficient. The men who designed the proximity fuse didn't set out to revolutionize warfare. They set out to solve a technical problem. How do you shoot down aircraft more effectively? The solution happened to inaugurate a new era of weapons that could sense and decide. That was the legacy. Not just the lives saved or the battles won, but the proof of concept. Machines could be taught to kill. Not just to carry explosives or fire projectiles, but to decide when to detonate, when to kill, based on sensor input and program parameters. When Germany surrendered on May 8, 1945, the proximity fuse program was declassified, not the technical details. Those remained secret for years. But the existence of the technology was acknowledged. Newspapers ran stories about the secret weapon that saved a fleet and the shell with a brain. The American public learned that their industry had produced a weapon so effective it changed anti-aircraft warfare. The British were more circumspect in their praise, noting that the initial concept had come from British research, but acknowledging that American production had made it viable. Winston Churchill, in his post-war writings, credited proximity fuses with proving potent against the small unmanned aircraft with which we were assailed in 1944. It was understated praise from a man not known for understatement, but it captured the essential truth. The technology worked. It saved London from worse devastation. The Soviet Union, which had not received proximity fuse technology during the war, despite being an ally, immediately launched its own development program. By 1946, a design bureau under Alexander Rasplet was tasked with producing a Soviet equivalent. They had newspaper accounts. They had fragments from German research. They had testimony from captured German engineers who'd examined Allied fuses. What they didn't have was the manufacturing expertise or the production infrastructure. The first Soviet prototype, completed in 1948, functioned but was clumsy, about 1.5 times larger than the American unit. Tubes too big, battery too heavy, reliability 60%. The engineers understood the principle. They could build devices that worked, but they couldn't achieve the miniaturization or the reliability that mass production required. It took another decade of development before Soviet proximity fuses reached American standards of performance. Other nations followed similar paths. Britain continued development of its own designs. France initiated programs. Even neutral countries began research, recognizing that proximity fuses represented the future of anti-aircraft and artillery technology. By the 1950s, the basic principles were widely known, but the manufacturing expertise, the quality control systems, the industrial processes that enabled million-unit production runs, those remained concentrated in nations with advanced electronics industries and extensive experience in precision manufacturing. The proximity fuse became a marker of technological sophistication. Nations that could mass-produce them were acknowledged as having world-class electronics industries. Nations that couldn't were dependent on imports or outdated defensive systems. It was a dividing line, not as dramatic as nuclear weapons, but equally significant for conventional warfare. Military analysts studied the V-weapon campaign for decades after the war. The lesson seemed clear. Technological superiority matters. Industrial capacity matters. Organizational competence matters. A weapon system is only as effective as the defensive systems it must overcome. If the defense can achieve 90% interception rates, the offense is futile regardless of how good the offensive weapon is. But there was a subtler lesson that took longer to appreciate. The proximity fuse succeeded not because America had better scientists than Germany or Britain, though it had excellent scientists. It succeeded because America had an institutional framework that could coordinate research, development, production, and deployment at massive scale. Section T brought together universities, corporations, and military services in a collaborative effort that none could have achieved alone. That framework, that organizational capacity, was itself a weapon, perhaps the most important weapon. Germany had compartmentalized programs, hierarchical decision-making, competition between services and agencies. Japan had similar problems. Both nations possessed technical knowledge equivalent to the Allies in many areas. Both lost the technological race not because they lacked intelligent people, but because their systems couldn't organize those people effectively toward common goals. The lesson should have been, organizational structure determines technological outcomes as much as individual brilliance. But this lesson proved difficult to institutionalize. Post-war military research programs often replicated the same compartmentalization, the same inter-service rivalries, the same organizational dysfunctions that had hampered Axis powers. The proximity fuse's organizational legacy was understood intellectually, but rarely implemented practically. Another lesson that emerged slowly was about technological surprise. German commanders who faced proximity fuse shells described feeling that the rules of warfare had changed without warning. Yesterday, foxholes provided protection from artillery. Today, air bursts rendered foxholes into death traps. The psychological impact of such sudden shifts in combat effectiveness exceeded the physical damage. Soldiers lost confidence in their training, in their equipment, in their ability to survive through skill and experience. Modern warfare would increasingly feature such moments. Technologies would emerge that invalidated existing defensive measures. Night vision making darkness no longer protective. Precision-guided munitions making concealment less effective. Electronic warfare making communications unreliable. Each innovation created temporary windows where one side possessed overwhelming advantage until the other side adapted. The proximity fuse was among the first such windows, and it remained open for most of the war, because Germany couldn't close it. They couldn't adapt because adaptation required industrial capacity they no longer possessed. That asymmetry, the inability to respond to technological surprise because your industrial base was being destroyed faster than you could rebuild it, that was the real lesson. Technological advantage is magnified when the losing side can't respond. Wachtel lived until 1982. In the decades after the war, he rarely gave interviews. He wrote no memoirs. He attended occasional reunions of former Flak Regiment 155W personnel, where they would discuss technical matters and avoid discussions of strategic effectiveness or civilian casualties. The men who'd launched the V-1s knew what their weapons had accomplished and what they'd failed to accomplish. They didn't need historians to tell them. One of Wachtel's subordinates, interviewed in the 1980s, mentioned that the colonel had kept a notebook during the war where he recorded daily launch totals and estimated success rates based on intelligence reports. After the war, Wachtel apparently burned the notebook. When asked why, he reportedly said, "Some numbers are better forgotten, but other veterans remember the numbers. They remembered launching 100 missiles and knowing that 10 might reach the target. They remembered the reports from the coastal observers, describing walls of air bursts over the English Channel. They remembered the transition from confidence to doubt to resignation as the interception rates climbed through summer and autumn of 1944. One veteran, speaking decades later, tried to explain what it felt like. We were doing our jobs. The V-1s launched properly. They flew properly. The guidance systems worked. Everything on our end functioned as designed. But they weren't reaching the targets. It was like throwing rocks at a wall. You can throw perfectly. The rocks can be aerodynamically sound. But if the wall is too strong, the rocks just bounce off. Except our wall was made of American radar and proximity fuses, and our rocks were expensive cruise missiles. We knew it was futile. But what else could we do? Stop fighting? Surrender? You do your job until you're told to stop or until the war ends. That veteran, like most who served in Flak Regiment 155W, never blamed the V-1 itself. The weapon worked. What failed was a strategic situation, the balance of technological capabilities, the industrial capacity. Germany was throwing rocks at a wall built by American industry. The rocks broke. The wall held. Today, proximity fuses are ubiquitous in military arsenals. Every modern military with significant anti-aircraft capabilities uses them. They're built into surface-to-air missiles, artillery shells, rocket-propelled grenades. The principles pioneered in 1940 through 44 have been refined and miniaturized further. Modern proximity fuses use laser range finding, infrared sensors, Doppler radar, sometimes combinations of multiple sensor types. They're more reliable, more precise, smaller, cheaper than the original VT fuses, but they're all descendants of that original technology. All incorporate the same basic insight. A weapon can sense its environment and choose its moment of detonation based on that sensing. The miniature radar in the 1944 VT fuse was primitive by modern standards, but it established the principle. Weapons could be smart. They could make decisions. They could achieve effects that dumb weapons couldn't. The line from VT fuses to modern autonomous weapon systems is direct and clear. If a shell can sense when it's near a target and detonate itself, why can't a missile sense targets and steer toward them? If sensors and decision-making can be built into munitions, why not build them into platforms? Drones, autonomous ground vehicles, loitering munitions that find their own targets, all are elaborations on the same theme. Put sensing and decision-making into weapons. Make them smart enough to achieve effects without constant human guidance. This trajectory troubles some observers and excites others. The optimists see increased precision, reduced collateral damage, more effective defensive systems. The pessimists see the gradual removal of human judgment from the decision to kill, the automation of warfare to the point where machines make lethal decisions at electronic speeds that preclude meaningful human oversight. Both are probably right. Modern weapons are more precise than their predecessors. Proximity-fused anti-aircraft systems can distinguish between aircraft and birds, can avoid firing at friendly units, can calculate optimal engagement ranges. This precision saves lives by reducing the number of shells needed to achieve effects and by limiting unintended casualties. But modern weapons also make killing easier, more abstract, more removed from human agency. The operator firing proximity-fused anti-aircraft rounds doesn't see the people dying, doesn't hear screams or witness suffering, just sees targets appearing on screens and disappearing when engaged. The mediation of technology makes psychological distance that would have been impossible when killing required direct physical confrontation. The V-1 campaign was an early demonstration of this dynamic. German launch crews sent missiles toward targets they couldn't see to kill people they'd never meet. British and American gun crews fired proximity-fused shells at missiles, not humans, focusing on the technical problem of interception rather than the ultimate consequence. Everyone involved was insulated from the direct act of killing by layers of technology and distance. It made the killing easier to perform and harder to confront morally. This is the world the proximity fuse helped create. Not single-handedly, obviously. Many technologies contributed to the abstraction and automation of warfare. But the VD fuse was among the first to demonstrate that weapons could sense and decide, that killing could be partially automated, that effectiveness could be dramatically increased by removing certain decisions from human operators and embedding them in the weapons themselves. The final accounting of the V-weapon campaign. V-1s launched at Britain, 9,521. V-1s launched at Antwerp in Belgium, 2,448. Total V-1s launched, 11,969. V-1s reaching target areas, approximately 3,200. Interception rate, approximately 73% of the intercepted missiles. Proximity-fused anti-aircraft guns accounted for the majority after July 1944. Exact numbers are disputed, but estimates suggest anti-aircraft guns destroyed approximately 60 to 70% of all V-1s shot down, with fighters and barrage balloons accounting for the remainder. British civilian deaths from V-1 attacks, 6,184. British civilians seriously injured, 17,981. If interception rates had remained at June 1944 levels of approximately 40 to 50%, deaths would likely have exceeded 15,000 and injuries 40,000. The proximity fuse saved approximately 9,000 British lives and prevented 22,000 serious injuries. American proximity fuses produced during the war, 22 million units. German proximity fuses produced approximately 1,000 prototypes. Soviet proximity fuses produced during the war, 0. Japanese proximity fuses produced during the war, 0. Cost per American VT fuse in 1942, $732. Cost per American VT fuse in 1945, $18. Total program cost, approximately $1 billion. Equivalent to roughly $14.6 billion in 2021 dollars. For comparison, the Manhattan Project cost approximately $2 billion in wartime expenditure. Ships saved from kamikaze attack due to proximity fuses. Estimates range from 30 to 50 vessels. Allied sailors' lives saved in Pacific Theater, 10,000 to 15,000. Enemy aircraft destroyed by proximity-fused anti-aircraft fire. Estimates vary, but likely exceeds 2,500 in Pacific Theater alone. The numbers tell a story of industrial mobilization, of technological advantage translating directly into saved lives and military effectiveness. They also tell a story of asymmetric capability. When one side can produce 22 million units of advanced technology and the other side can manage 1,000 prototypes, the outcome is predetermined. The story of the proximity fuse and the V-1 campaign isn't fundamentally about technology. It's about capacity. The capacity to mobilize industry. The capacity to organize expertise. The capacity to translate scientific knowledge into mass-produced weapons that actually work in combat conditions. The capacity to sustain programs over years despite setbacks and challenges. The capacity to adapt defensive systems faster than the enemy can adapt defensive systems. Germany lost that competition, not because Germans were less intelligent or less capable or less determined, because Germany, by 1944, no longer possessed the industrial infrastructure or the organizational stability to compete. The Allies, particularly the United States, did possess those things. The result was a technological gap that made 90% of V-1s fall from the sky. Max Wachtel learned this lesson watching his weapons fail. The engineers who analyzed captured proximity fuses learned at examining miniaturization they couldn't replicate. The soldiers who died under proximity fuse artillery barges learned it in the last moments of their lives. The lesson was simple and brutal. In modern warfare between industrial powers, the side with superior production capacity wins, assuming reasonably competent leadership and strategy. That lesson remains relevant. Today's conflicts still feature asymmetries in technological capability, in industrial capacity, in organizational competence. The specifics change. The underlying dynamic remains. The side that can produce more, adapt faster, and field superior technology consistently has overwhelming advantages. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The proximity fuse was a marvel of engineering. But more than that, it was a demonstration of what coordinated industrial and scientific effort could achieve when properly organized and adequately resourced. That demonstration changed warfare. It changed how nations think about weapons development. It changed the standards for what's considered possible. When 73% of enemy missiles fall from the sky, you achieve dominance. When 90% fall on good days, you achieve something approaching invincibility within that specific domain. The Germans believed such interception rates were impossible until they watched them happen. The Japanese believed miniaturized radar was unfeasible until they analyzed the fragments. Both learned too late that impossible just means we haven't solved it yet. The Americans solved it. The British provided the initial insights. Together, they produced a weapon that saved London, protected Antwerp, shielded the fleet, and helped win the war. Not through a single dramatic breakthrough, but through thousands of small improvements, through systematic quality control, through relentless production scaling, through the unglamorous work of turning laboratory prototypes into battlefield realities. That's the real story. Not genius scientists having eureka moments, but thousands of workers assembling tiny components under microscopes. Engineers solving mundane manufacturing problems. Military officers integrating new weapons into existing operational frameworks. The boring, systematic, organized application of industrial capacity to military problems. The proximity fuse won because America had 35,000 people working on it and the organizational structure to coordinate their efforts effectively. Germany had brilliant researchers working in isolation without the resources or time to translate knowledge into production. That was the difference. That's always the difference in industrial warfare. The V-1 campaign failed because it encountered a defense it couldn't overcome. The defense existed because one side possessed advantages the other couldn't match. Those advantages weren't primarily technological. They were industrial, organizational, systemic. The technology followed from the systems. The systems determined the outcome. Wachtel commanded the V-1 offensive. He did so competently, adapting tactics as circumstances changed, working within the constraints he faced. But he was commanding a weapon system designed to overcome defenses that existed in 1943. By mid-1944, he was fighting defenses that belonged to a different era of warfare. His weapons were obsolete before they reached combat maturity. That's the cruelest aspect of technological surprise in warfare. Your weapons can be advanced, well-designed, properly employed, and still be completely ineffective because the enemy has developed something you didn't anticipate and can't counter. The V-1 was a technological achievement. It was also a failure. Both things were true simultaneously. The proximity fuse was the reason for that failure. A tiny radar in an artillery shell, deciding when to explode based on electromagnetic reflections from a target flying at 400 miles per hour. It sounds like science fiction. In 1940, it was considered impossible. By 1944, American industry was producing 40,000 per day, from impossible to commonplace in 4 years. That's the power of organized industrial effort. That's what won the war. That's what made 90% of V-1s fall from the sky over the English Channel. their missions unfulfilled, their targets unharmed, their threat neutralized by invisible shells that knew, with electronic certainty, when to explode.